Okay, so welcome back. And it's a pleasure to introduce Mathew Young from Texas A&M University. He will speak on large sieve inequalities for families of automorphic forms.
Okay, thanks for the invitation to speak here. I'll probably go a little slower than normal. It's a little early in the morning for me. That's probably okay if I go a little slower than I normally would. Also, I just want to say, so I can't see chat or anything right now. So if anyone has a question, you'll have to just speak up and interrupt, and that's perfectly fine. Okay, so let's just jump into the problem here. So to start, let's set up some notation. So I want the script F to be a family of automorphic forms. And I'll give examples of what I'm interested in a little bit. And for an automorphic form, I want to write its L function as so. And so the lambda f of n are the Dirichlet series coefficients of the L function. That's the main thing I want to get across in this slide. So now, yeah, I'm very interested in families of L functions, and there are many interesting questions we could ask about a family of L functions or automorphic forms or either one. And so here are some questions that we're interested in. So I think the most basic question we could ask about a family is just how many elements are in the family. So this could be a version of Weil's law. Next level of difficulty is to study low-lying zero statistics. So the distribution of zeros near the central point. And then the kinds of things that I think we've been hearing about it at the conference. Unfortunately, I've been asleep during the conference, but I know people have been talking about subconvexity bounds for L functions, and so one of the questions we might ask about a family of L functions is just to be able to bound a moment of the L functions, or get an asymptotic for that. And then in some ways, an even more difficult problem, not in all ways, but in some ways, a more difficult problem is to get a large sieve inequality for the family. So a large sieve inequality can imply certain bounds on moments, and so in that sense, it can be more general. Okay, so what is a large sieve inequality? So it's a bound of the following form. So so it's like a double sum. You have a sum over the elements in your family, and then also a sum over the Dirichlet series coefficients. So your lambda f of n's. And here, an is just a completely arbitrary, say, vector and or tuple of real numbers. And so on the left-hand side of this inequality, this is like it's like you take one way to think about it is you could take a vector of your coefficients, and then you take the inner product or the dot product with the vector of an's, and then so that's what that inner sum over n represents, and then you take the length squared of that, and then you sum that up over the family. So, okay, and so that's the kind of thing that we're looking at. In some sense, it's testing the correlation of your lambdas, your Dirichlet series coefficients against this one vector of an's. And so then we're looking for a bound in terms of the L2 norm squared of the coefficient. So we scale by that, and then the norm is this delta of Fn. And it's in the context of the large sieve, it's important that we get a bound that's valid for all choices of coefficient. So an's have to be completely arbitrary real numbers. And of course, we'd like to prove this with this number delta as small as possible. So if you're only interested in bounding moments of L functions, that would mean that you might be looking at an as like 1 over square root of n, or maybe a divisor function divided by square root of n, or something like that. And so that's what I mean by the large sieve is even more general. We have to treat more general coefficients. Okay, so if we get a good bound on this, so if delta is small, then this is saying something very strong about our family. It's some kind of quantitatively strong orthogonality for the coefficients of the family. Okay, so now one of the most important tools in this area is the duality principle. So the duality principle, basically it lets you swap the roles of your family. So in the context of the large sieve for families of automorphic forms, it lets you switch the role of your family and the sum over your family and the sum over the integers n. And so in greater generality, this is just a fact in linear algebra about, let's say, about matrices or operators. And so this duality principle just says that these two norms that I've written down are the same. So you can, in one of these, it's like you're taking your matrix of AMNs against a vector on the right, and the other one is like you're multiplying by a vector on the left. And your AMNs might not be a square matrix, and so these might be completely different sizes. Okay, so that's the duality principle. So in the context of automorphic forms, it means that these two norms, one where you put the sum over the family on the outside and the sum over little n on the inside, is the same as taking the sum over n on the outside and the family on the inside. But this is, I want to emphasize that this is true. This equivalence is true because we're looking at arbitrary coefficients. So one inequality being valid for all vectors is equivalent to the other one being valid for all vectors. So it's kind of having to work with arbitrary coefficients makes the problem harder, but it also lets you use the duality principle. So that's a big gain. Okay, so here are some examples. So this will give some examples of what I mean by families of automorphic forms as well. So the most classical example is the large sieve inequality, the classical large sieve inequality. Here I've stated the multiplicative version where we have Dirichlet characters. So it's just the family of all Dirichlet characters mod, or primitive Dirichlet characters mod q, and the little q goes up to capital Q. So that the cardinality of this family is roughly q squared. It's a bit less than that, but it's grows like q squared. Right, and so this is a well-known and very important and very strong bound for this family. So there are many applications. So the Bombieri-Vinogradov theorem about primes in arithmetic progression uses the large sieve. If you ever wanted to bound a moment of twists of L functions, you could use the large sieve for that. So the Bombieri-Vinogradov theorem tells us that the primes are well distributed in arithmetic progressions in a suitable average sense. And it's similar in strength to the generalized Riemann hypothesis. So we're able to prove strong things about primes in arithmetic progression on average. Yeah, so I did want to say, so the large sieve inequality doesn't let you prove subconvexity for an individual L function on its own, but there are problems where you take like a moment of L functions and then you do some transformations of the moment and get a dual moment or some other kind of like maybe using some kind of spectral reciprocity for the moment. And anyway, so an example would be like Monohashi's formula for the fourth moment of the zeta function. It transforms the fourth moment of the zeta function to a cubic moment of Moss form L functions on GL2, and then this dual moment you could then study or try to bound using a large Sieve inequality. And so in some of these moment problems, after some transformations of your family, then you get a dual family, and then a really strong way to finish the process is to use a large Sieve inequality at the end. The large Sieve inequalities can play an important role in subconvexity proofs. Okay. So another example of a large Sieve inequality is a theorem of Heath-Brown. So here he has these quadratic characters. So you can think of n and q as ranging over, say, odd square-free integers. That's what the star represents. And so this is a small subfamily from compared to the classical large Sieve, because we're only selecting the quadratic characters. And yeah, and so the bound is, so instead of q squared plus n, it's roughly q plus n. There's an extra q times n to the epsilon power. But yeah, it still has this shape of the number of elements in the family. That's the q, and then plus the number of elements on the inner sum, that's the n. So this is also useful for bounding, say, quadratic twists of L functions. It's particularly interesting to look at quadratic twists of elliptic curves, and then this has some applications there. So GL2 family is the following. So there's a theorem of Désier and Ivanietz from, I think, 1978, 1979, where let me say what this is. So you have a GL2 family of Moss forms. It also works for holomorphic forms, but I think I've just stated it for Moss forms here. So you have Moss forms of level Q and spectral parameter T sub f going up to capital T. In this version, we want to weight things with basically with like the Peterson-Kuznetsov type weight, which is this residue of this Rankin-Selberg L function. Anyway, so you put on that weight, and then the bound is qt squared plus n. So again, so Weil's law will tell us that the number of elements in the family is around q times t squared. So this is similar to the previous ones where the bound is the size of the family plus the number of terms on the inside. Okay, so all of the bounds that I've stated so far take this form. So it's this cardinality of the family plus n, and it's well known in the area that this kind of bound is optimal. So if it's true, it's optimal. Okay, so this is the best possible bound you could hope for. It's not hard to show that there's a lower bound on this norm that's at least the size of the family, and also it's at least n. So so it's at least the sum of the two up to constants. Okay, so proof of this is just comes from the fact that the proof of the optimality, I mean, it comes from the fact that so in the definition, you can always choose your vector to correlate perfectly with one element in your family. And so there's exactly no cancellation for at least one element in the family. And that gives you a lower bound. And then by duality, that it gives you the sort of the complementary one. So so it has to be symmetric in these two parameters. Okay, so based on these examples, you might start to think that that we get these bounds just all the time. So whenever you have a family, you just you might have to work at it, but you should get the size of the family plus n. So actually, so I've been calling this the optimistic bound. So the optimistic bound is this one. So it's the size of the family plus n. Let's put on a little epsilon safety valve there, just for safety. But so let's call this the optimistic bound. So it's optimistic because it's the best you could hope for. I'm not calling it the, well, whatever. Okay, so it's optimistic bound. So there's a theorem of Ivanitz and Xiaoxing Li from 2007 showing that so if you look at the family of gamma 1 of Q, so Moss forms on, or holomorphic forms on gamma 1 of Q, let's say with Q prime and let's say fixed weight, like weight 2, then this does not satisfy the optimistic bound or conjecture. So this is a, so if Q is a prime, then everything in this family consists of new forms. So nothing comes from lower level. And so there's no issues with multiplicity or anything. And so this is a genuine counterexample to the optimistic bound holding. The actual bound is a little more complicated to state, and I don't need it. But they give, yeah. You should look at their paper. It's interesting. You can find the full result there. So that's the first example I know of. But since then, there have been a number of other kinds of ways that I guess that the optimistic bound can fail to be true. So this kind of for me, this makes life kind of exciting because we don't know what the truth is. And so so for each family, we have to sort of take it in and see what's going on. And yeah, it's not even clear what's a conjecture for a given family. So here's a class of examples. So in many cases, like in the Desier-Ivanitz case from the previous slide, let's go back. So this one, so this is, I stated it for cusp forms, but really the same bound holds if you put the cusp forms and Eisenstein series together. And the proof naturally deals with both at the same time because it uses a Kuznetsov formula to transform the problem into sums of Klosterman sums. And so in that sense, that you might as well put the cusp forms and the Eisenstein series together because that's what appears on one side of the Kuznetsov formula. Okay, so there are cases where, especially in higher rank, so Blomer and Butt-Kane showed this for the family SLNZ with n at least 3, then the Eisenstein series themselves, so just forget about the cusp forms, just look at the Eisenstein series, they can be problematic. They can be large enough to give a counterexample to the optimistic bound. Another kind of example is what I call that a family could have a large biased set. So what I mean by this is the following. So let's say, basically, for a good way to think about this is like you might imagine that for every element in your family, you can select. Oh, sorry. So before you, so there exists some set, the script n, such that basically if along this subsequence or along this subset, there's very little cancellation in your Dirichlet series coefficients. Okay, so your sum over little n of your m to f of n, there's basically no cancellation. So you get the size of this biased set, and then imagine this is true basically for every single element in your family. If this is true, if you have a reasonably sized bias set, so like if n is at least the size of the family to the 1/1,000,000 power, then this would be enough to be a counterexample to the optimistic bound. So a very simple example of a bias set is if you go back to Heath-Brown's problem where we have quadratic characters. So if your family consists of quadratic Dirichlet characters, then the bias set would be the squares. So the inner sum, the sum over little n, would be the sum over the squares. So there's no cancellation along the sum of squares, and for every single element in the family. And so this is a biased set of size around the square root of n. So it's a very large biased set. Now this does not contradict Heath-Brown's result, because Heath-Brown assumed that the inner sum was over square free numbers. And this is basically why that he has that condition. So anyway, so biased sets can be difficult to detect, but they exist in some cases, and then they can lead to a large size in this large Sieve inequality. Yet another reason. So there's a recent work of Alex Dunn and Maxime Radziwi, where they looked at so they revisited a cubic large sieve that was due to Heath-Brown. So Heath-Brown got to study the cubic version of his quadratic large sieve, and but the result wasn't as good. It wasn't. He did not get the optimistic bound for the cubic case, and it turns out that that bound cannot be improved. So there is a subtle bias in this family that was recently discovered by Dunn and Radziwi. So this is another another kind of bias. So yeah, so this, I don't know, I think this is interesting that there's all these reasons that the norm can be kind of big. Okay, so the main family I want to talk about in this talk is the following. So it's a GL2 family of Eisenstein series. Okay, and the Eisenstein series I want to study will have a varying level. So if you go back to the Désier and Ivanitz family, it was all Moss forms and an Eisenstein series of level Q, and that Q was not varying. I mean, you could sort of they weren't summing over Q in their family. Okay, so they weren't looking at multiple levels at the same time. So so this family, it will have varying levels, and but it's an Eisenstein series family, and it's a family that have a trivial central character. Okay, so this kind of avoids the kind of problem that came up in the Ivanitz and Lee family. So that was the gamma 1 of Q family. So modular forms on gamma 1 of Q, those break down into modular forms on gamma of 0 of Q with different central characters. And so yeah, so that's the reason why you might want to look at trivial central character. So because we know that if you start changing the character, then there's some possible bias there. Okay, so the Eisenstein series of that I want to look at are the new form Eisenstein series. These are on the Eisenstein series side, these are just the same as new forms on the cusp form side. So they're the Eisenstein series that don't come from lower level. And so there's a known classification of these Eisenstein series, and you can very explicitly write down their Dirichlet series coefficients or their Fourier coefficients on the Eisenstein series side. And basically there are these, well, I have the formula written here. So it's some kind of sort of twisted divisor type function. So this lambda chi it is so you factor n in all possible ways is AB, and you get chi of A and then chi bar of B. And then I mainly want to study t equals 0 here, but so if you're more used to like the level 1 Eisenstein series, that would be like taking chi to be trivial, and then it is your parameter that's changing, and you get this kind of twisted divisor function, or it's twisted by this it factor. Okay, so these are the coefficients that I'm interested in for this talk. So let's define the norm. So this delta of Qn is the norm of this family. So I want to sum over all primitive characters chi mod q, and then sum over these little q's. So it kind of looks like the GL1 large sieve on the outside, but then what's different is that we have, instead of just chi of n, it's this twisted divisor function, this lambda chi it of n. But here I'm taking t equals 0, although I have a more general result for varying t, but this is just for simplicity, just take t equals 0 in this talk. Okay. So just as a warm up, or to sort of see what's going on here, I claim that there's if you sort of apply the classical large sieve, you get some kind of bound, but it's not the optimistic bound. Instead of q squared plus n, you get this q squared times the square root of n, and then you get an extra n log n. So instead of just n, it's n log n. But the main thing is you've got this q squared times the square root of n. So it's much, much bigger than the size of the family there. It's the size of the family times square root of n. So, okay, and so where does that come from? Let's see, I think I have so I say it on the slide. So if you want to, I think the easiest way to see this is to use duality. So you move the sum over n to the outside and put the family on the inside. And then the sum over n, so it's really like a sum over a and b, like these, with the divisors, and you just use Dirichlet's hyperbola method. So let's imagine that a is the symmetric in a and b. So let's say a goes up to square root of n, and so it's like the smaller one. So put that on the outside, and then the sum over b, you apply the classical large sieve to. And then it's this outer sum over a that forms this extra square root of n in the first term. Okay, so this is like just as a warm up. This is the first bound you might get, but actually, some thought shows this is the best possible for this particular family. And the reason is that there's a biased set. So if you take, going back to the definition, so if you take n to be let's say a prime squared, then you get the sort of the diagonal where a is equal to b, is equal to the prime. Then there's no cancellation, like, yeah, the chi's cancel out, the a over b to the its cancel out, and so really it's just saying that this lambda of a p squared is 1 plus chi squared of p plus chi bar squared of p. And the chi squared of p and the chi bar squared of p, basically they cancel out. So if you sum over the characters, that part averages out to 0, but the 1 is biased for every element in the family. So this is similar to Heath-Brown's family, where the primes, let's say the prime squares form a biased set of size square root of n, or square root of p, in this, the way I've labeled it. Okay, so this means that so the size basically it's square root of p or square root of n. That means that this classical large sieve inequality is basically the truth. Okay, there's really no way to improve on what you get from the classical large sieve for this family. So so in that sense, we're done. But what it means is we should sort of do what Heath-Brown did, which is in the quadratic character case, which is to impose a condition that avoids the bias. Okay, so let's redefine or take another stab at it. So let's take the same definition as before, but put on a condition. So here, let's put on the condition that A and B are relatively prime on the inside. So that's the only alteration I've made to this definition from before. I just put on the condition that A and B are relatively prime. So that avoids the biased set. So that's maybe the easiest way to avoid the biased set. Okay. So then now with this family in this definition, then the main result I want to present is the optimistic bound for this family. So the bound is that this thing is bounded from above by q squared plus n to the 1 plus epsilon. So this is similar in strength to the classical large sieve, although there's this extra epsilon factor, which seems to be pretty hard to avoid. Okay, so that's the result. So I also wanted, before going off and saying anything about the proof, I wanted to reinterpret this bound in a different way. So it's just another way to look at the exact same thing. Okay, so let's define, so people have been complaining about my notation here. I forgot to change it. So this q sub q is not the p-adics. This is just it's just the rational numbers where none of the denominators are not divisible by any prime in q. Okay, so that's what that is. It's a localization, if you like. Anyway, it's not the p-adics. And yeah, anyway, so that's what this is. So it's rational numbers where the denominator is co-prime to q. And this is a ring. And we have a reduction map on this ring. So you can reduce mod q in the set. And then we can define, and this is a ring homomorphism. The reduction map is a ring homomorphism. And then for an element in this ring, we can evaluate the character. So we can evaluate a character at a rational number just by taking the reduction. So really what's going on is like chi of a over b just means chi of a times chi bar of b. Okay, so that's really all that's going on here. As long as b is not divisible by q. So it's really like chi of a over b. Okay, so then I also want to define a kind of a height function. I don't think it's really what people would call a height function, but it's some measure of the size of this rational number, which is just the absolute value of a times b, if you've written a over b in lowest terms. Okay, so this is just some notation to get started. Then with this notation, the theorem I just stated, this large sieve bound is the following. So you've got your sum over q and chi, that's your sum of your family on the outside, and then you've got a sum over, now it's rational numbers in this set. So rational numbers where you can reduce mod q just fine. And then with this height going up to capital N. And then we can take a vector indexed by these rational numbers and evaluate it at chi of n there. And yeah, this is the bound. So this is just exactly the previous theorem, just restated in this notation. So I've been calling this the rational large sieve. Okay, so here's an application. So if you ever wanted to sieve rational numbers, now we have a version of the arithmetical large sieve for in this context. So let me state what this says. So maybe just to pause for a moment, the classical, I mean, it's kind of a funny, you know, in the history that the naming of things is a little funny. So so far, you know, everything I've been calling a large sieve, you might have wondered, like, why is this called a sieve if there's no sieving? And so there's this, I guess now it's become kind of separated. It's been common, or it's become kind of a convention, I think, to give different names for different parts of things. So the analytic, what I've been calling the large sieve inequality, you might call the analytic large sieve. It's just it's a bound on an operator norm of some matrix. And then one can deduce what you might call the arithmetic large sieve, which is an actual sieving problem. And so that, okay. So this is the arithmetic. This is the version of the arithmetic large sieve in this context. Okay, so let me set this up. So let's define this script n to be the set of these rational numbers with height up to capital N. I want to take a finite set of primes. That's a set P. For each prime in the set, I want to take a subset of Z mod P. That's this capital omega P. Let's let little omega P be the cardinality of this family. And then just define this function H of P, which is omega P over P minus omega P, and then extend this multiplicatively over square free numbers. And then now the sieving question is to ask how many elements are left in the family after you sort of throw away any element that lands in one of these omega P's. So that's what this script S set is. And the bound, the arithmetical large sieve bound, is that the cardinality of the set is at most n plus q squared to the 1 plus epsilon, all divided by h, where h is this quantity. So if you're familiar with a classical arithmetic large sieve, this looks basically identical. And the proof is basically identical to the classical case. So if you haven't seen the classical case before, this is probably a lot, and you can basically ignore this for the rest of the talk. Like all this notation, like it doesn't come up again later in the talk. But so one of the standard applications here would be like, let's say you just threw away half of the residue classes mod P. So for all primes up to say square root of n, you throw away half of the residue classes mod P. And then you ask, okay, how many elements are left in your family? And so then the bound that you get is roughly square root of n, or n to the half plus epsilon. And this is basically sharp, as can be seen by looking at the set of squares. So if this is like the standard or a classical application of this. So like the squares. Yeah, so the squares are squares mod P for every single prime P. So if you throw away the non-squares mod P, then you see what set is left over. And the squares are definitely in there, but there might be some other elements too. But this says there can't be too many other elements in there as well. Okay, so this is just supposed to be a nice application of this new rational large sieve inequality. Okay, so now let's talk a little bit about the proof of the results. So it breaks down into three separate results. Each one is independent, and the three of them together can be used pretty easily to prove the main theorem. So the simplest one of these is a monotonicity result. So if you, this basically says that this delta norm is monotonic in either component. And this is the precise statement. Okay, so you can always extend one variable to be longer if you want to. And this turns out to be beneficial in some situations when combined with some other moves. So here's the idea for the monotonicity. This is using an idea that goes back to Forti and Viola from 1973. So let's say we want to prove monotonicity in the n variable. So what you do is you just average over a set of primes. So this first line that I have displayed here is a tautology. There's nothing going on. I'm just summing over a set of primes, and then P star represents the number of primes that I've summed over. And so those just cancel out, and then I haven't done anything. But then going to the next line, what I've done is just said, okay, well, absolute value of chi of phi squared is 1, except when it's 0, which is very rare. So if you can sort of take account or control when it's 0, then you can get to the second line. But then now if you look at that inner sum, you can think of A times P as a new variable. So it's running over a set of integers that is now bigger than before. So the integers now are of size P times N rather than size N. They're sparsely supported, they're supported on the multiples of P, but that's how big they are. So then you could just use the definition of the norm for this particular sequence, a sparsely supported sequence. And basically that's the idea. And you can get this monotonicity bound from that. And the same idea with some modification works on for the Q aspect. Okay, so that is the monotonicity result. That's the easy part, but it's also important. Now the other two parts, the other two main results attack the problem from both sides. So there's so we have access to the duality principle, so we can take the family on the outside, or we can take the sum over n on the outside. And you would like to, or it's beneficial to use one method over the other depending on how the parameters are arranged. So basically, you should take the sum over n on the outside if n is big. Okay. Because that means you have a larger averaging set, and that should make that more powerful. And so basically the only move we could try, I mean, that I can think of would be the functional equation. And so let's see what happens there. So I've put in red the condition that the GCD of A and B is equal to 1. This is a necessary condition, but it's hard. So red means difficult or problematic. So remember, if we don't have this condition that the GCD of A and B is 1, then we have this problem where we have this biased set. So we definitely need this condition, but it causes problems. So if you just take that sum, square it out, you get the second line there, and then the third line comes from applying the Mellon transform and writing things in terms of L functions. So it's kind of rigged, or it's set up so that the product of L functions that we get is self-dual. So each one all by itself, like this L of S chi1 chi2 bar, is not self-dual, but the product of the two L functions is. So if you apply the functional equation to one, it sort of gives you the other one, and so you get this switch. Anyway, that's just a side comment. So the key thing is that, or the key thing I want to point out is that this condition that the GCD of A and B is 1 causes a zeta of 2s to appear in the denominator. So if you want to apply the functional equation, that's going to involve shifting contours off to the left, and zeta of 2s being in the denominator is problematic for that. So even if you assume the Riemann hypothesis, that still only lets you basically move to the 1/4 line, and that's you still even assuming the Riemann hypothesis, you run into problems of all these poles of the zeta function coming from the zeta function in the denominator. Okay, so this is a problem, but we also know we need to handle this condition somehow. So how can we get around this? So, okay, yeah, so this is what I just said about this condition, GCD of A and B is 1. So how do we get around it? So we put on a compromise. So instead of dealing with the condition that A and B are relatively prime, let's weaken that condition, but still try to get something with it. So that's this condition in orange, that A times B divided by the GCD of A and B squared. Let's take that to be bigger than some parameter y, where y we get to choose. Yeah, so if A and B are, this comes from positivity and the fact that if A and B are relatively prime, then that AB over GCD A and B squared just becomes AB, and so we're taking AB bigger than y, and that's just redundant if y is small, or we're a little bit smaller than n. Okay, but this is really, I mean, if you think about it, so AB is of size n. So if you sort of rearrange this condition in orange, it's giving us an upper bound on the GCD of A and B. So it's no longer saying that GCD is 1, but that it's not too big. So it's giving us control on the size of the GCD. So this form of the upper bound, like this kind of approach to things, was used by Heath Brown in his proof of the quadratic large sieve. He had exactly this kind of issue. So he had to sum over square free integers, and he wants to use a functional equation or Poisson summation. And Poisson summation is not just given for square free integers. If you want square free integers, you would need to sieve, just like we did here. What we would need to do here if we wanted to deal with this GCD condition. And so he used the same kind of compromise. Okay, so now once we put on this compromise, then the idea is to use inclusion exclusion. So we have this condition, this condition in orange. So let's just think of that as just omitting the condition and then subtracting off the terms where this ratio AB over GCD of A and B squared is at most Y. So that's what this S infinity and the S less than or equal to Y represent. And so these two terms we're going to deal with completely differently, completely different techniques. So S less than or equal to Y, what happens is you just square it out. You get this. So if you factor out the because I guess I'm not squaring it out. I'm using the Mellon inversion formula, and I'm changing variables. So I want to sort of go back to where I started from, like the original expression, but where we have in that original expression, we need that our A and B are relatively prime. So if you imagine like just factoring out the GCD of A and B here, that sort of GCD variable forms a zeta of 2s. So that's where this zeta of 2s comes from up in the, now it's in the numerator. Okay, so we've got the zeta of 2s, that's there. And okay, so now the idea is we're going to shift contours to the left. And so if we do so, so if you look at about shifting to the left, there's a pole of zeta of 2s at s equals a half. And that's basically unavoidable. If we hadn't, maybe I shouldn't say too much, but like that red zeta in the denominator, in a sense, is like the way we're handling it is now kind of coming up into the numerator. Anyway, so we get a pole at s equals a half, and if you just write that down, that's what this polar term is. And if you just try to bound it all by itself, it's just too big. It's too big to be consistent with the theorem that we're trying to prove. Okay, so that's the bad news. But the good news is that on the new line of integration, you get something good. Like the new n sum goes up to some parameter y, and y is smaller than where we started. So it's a gain on that side of things. And so we've got a polar term. Let's just leave it alone. We can't estimate it now. Let's come back to it later. Okay, so that's that part. Now the other side, the sort of the dual side, is, we'll call it S infinity. And that's where we have the sum over all A and B. So I put that in green because now there's no condition. We can just sum over all these integers. And we get the L function. I'll try to be a little more brief. The details get a little more messy here, but basically I just want to apply the functional equation. So I guess a barrier to the functional equation is that so chi1 and chi2 are assumed to be primitive, but that doesn't mean that chi1 times chi2 bar is primitive. And there's various ways this can fail. They could be equal to each other, or they could have or or maybe some parts of them are like they partly cancel, but not entirely. Like there's all sorts of different things that can happen. And so that's kind of complicated. So for this talk, let's just deal with the two extreme cases. So the two extreme cases are where the characters are either equal, or let's just say their moduli are completely co-prime. Those are the two extreme cases in practice. We have to deal with everything, of course. So the diagonal is pretty easy to understand. That gives you basically zeta of s squared, and that's perfectly fine. You get like basically n from that. That's consistent with the large Sieve inequality. And then from Q1 and Q2 relatively prime, and you use the functional equation. So I kind of want to skim over this because the details just get a little bit messier, but like there's just too much notation to try to take in, I think. But basically the idea is just to apply the functional equation and convert back to where we started from. So the L functions, when you apply the functional equation, you get the same L functions back. I mean, each character gets conjugated when you apply the functional equation, but since we have them in pairs, the product stays the same after the functional equation. And basically, we can chop it off. This like we're used to. The dual sum has length, the conductor over n. In this case, the conductor will be size q to the fourth. So we can chop it off at q to the fourth over n. Okay, so this indicates that, let me just say it back. So if n is a little bit bigger than q squared, then this method should be good. It will reduce the length of summation. Okay. Yeah, then there's this issue that after the functional equation, we want to get back to this GCD condition so we can return to our original norm. So we have to factor out this GCD. That gives you another zeta of 2s. So then just going, I know this is brief, but you get another zeta of 2s from factoring out the GCD, and then we want to move the contours back to the line 0. And again, we get this pole at a half. And it's kind of, there's this miraculous cancellation that happens. If you choose y appropriately, the two polar terms cancel each other out. And the new line of integration is, you get a good bound on that as well. So this cancellation of these polar terms also occurred in Heath Brown's work on the quadratic partition. So this is similar to that. So it's for me, it's kind of amazing how this all comes together and this cancellation of polar terms, etc. But yeah, okay. So the main result, so just to sort of summarize what happened, the main result on the functional equation side is a relation of the norm with itself, but with different parameters. And if n is bigger than q squared, this is basically a good direction to move in. It reduces the length of one of the parameters, that basically the n parameter. So that's what you get from the functional equation. So this is the second main result. So the third one I won't spend nearly as much time on. So let's just state the result. So on the other side, so the other main result is another kind of recursive bound. So this one says that it's bounded by q squared plus q squared over n times delta n over q n. So this is keeping sort of n the same, but the family is now changing. So this will come from looking at the problem on the dual side, where we have the family on the outside and n on the inside. And this should be a good technique to use if the family is big compared to n. So if q squared is big compared to n. Okay, so just to say what was briefly what's going on. So we need that the characters are primitive. So that's in red. So if we just try to square this thing out and use orthogonality of characters, the primitivity condition gives us a Mobius function here, and which leads to a zeta downstairs. So just look at the red text. Don't worry too much about everything else, but just look at the red text. This is giving us a zeta in the denominator, and this is a lot like the zeta of 2s in the denominator we had before. So the condition, like this condition that we want primitive characters so it's necessary, because if we don't have primitive characters, we get the same like trivial character, let's say, over and over and over again for every single Q, and this is a problem. But on the other hand, if you actually impose the condition that they're primitive, it also causes difficult technical problems. And in this framework, it leads to a zeta in the denominator that we just can't really handle. Okay, so to get around this, let's use the same kind of ideas as on the functional equation side. Let's put in a compromise. So let's, instead of imposing the condition that chi is primitive, let's just impose a weaker condition that the conductor is at least y for some parameter y. So this is using positivity. And then now let's use inclusion exclusion. So we'll extend this to everything and then subtract off the terms where the conductor is at most y. It's very much the same spirit as the previous case. So just to sort of quickly go through what happens. So for the first part, so the truncated part, this is the same idea as before. We want to go back to where we started from. And so we've relaxed we have a weaker condition. We just know that our characters have conductor at most y. You just sort of factor out the primitive part of your character, and then you've got this trivial part that you just sum over, and that gives you a zeta. So that's where this zeta of s comes from. And now it's in the numerator. This is very much analogous to the zeta of 2s that we had in the numerator on the dual side. All right, so we want to do the same thing, shift contours over to the left. This time we get a pole at 1 instead of at a half, it's at 1, but it's basically the same spirit of things. So there's this annoying polar term that is big all by itself, but let's just leave it alone and hope that it cancels out. And then the new line of integration is just fine. The family is shorter than before, so we're good there. And then now for the sort of extended part where we've got all characters mod q, then we use orthogonality to say that, if you sum over chi mod q, that's going to form a congruence or divisibility condition. So that's this condition that q divides a1b2 minus a2b1. Okay, so you just imagine squaring this out, summing over chi, you get a congruence. So now it's an important point that the diagonal forces a1 to equal a2 and b1 to equal b2. This is kind of a technical point, so let's just skip over that. So now the idea is inspired by a paper of Conry, Ivanits, and Ramanujan on it's called the asymptotic large sieve. They're studying a different problem, but it has to do with the large sieve inequality. And they use this idea that so if you sum over characters, you get this divisibility condition. And what you can do is called the divisor switching trick. So you sort of go to the complementary divisor. So what that means is you write, let's say, a1b2 minus a2b1 is q times r. And if q is big, then r should be relatively small. Okay, and so that makes it beneficial to use the complementary divisor, to use r instead of q. So basically everywhere you see q, you want to eliminate it and write things in terms of r instead. So I think this is very much the same as the functional equation of L functions on the dual side. It's just comparing the two methods, that this is how they kind of line up, and there's some other reasons to think of it as similar to a functional equation. But I won't say more about that right now. So just since I'm running very low on time, and I know this is a lot of notation to take in, basically you just plug this in, you switch divisors, go back to where you started from, you get some things, and you get a new polar term. That polar term is going to cancel, and then the new main term has smaller parameters than before, and it leads to that theorem I was saying. So okay, hold on. So that's this third theorem that I stated. Okay, scrolling back. Yeah, so it's this one. So this is the third main theorem, and then it's a pretty easy not too difficult exercise to prove the main theorem, like the total bound, using the monotonicity, this family sum one, and this other functional equation one. So these two recursive bounds. So it's kind of a pleasant exercise to deduce the main theorem from these three. You don't need to know anything about how these were proved in order to do this deduction. But that's the basic way that this all goes. And yeah, so I think I'm out of time, so I'm going to stop here and say thanks for your attention.
Yeah, thank you, Matt. Very nice talk, very interesting. So questions? Okay.
Hello? Yeah. Is there anything interesting happening if you just keep applying your main theorem recursively, like theorem 2 and 3 that you mentioned? Just keep on applying it on the right hand side. I mean,
so if yes, well, so yes and no. So if you don't, yeah. So that's the idea how it works. But there's a in between. You have to use the monotonicity. So if you don't use the monotonicity, you're in trouble. So you keep recursively applying these two, but in between you might extend one of the sums in a beneficial way. Mm-hmm. And so one of the ways you can see why you might get stuck if you only have these two theorems here, these two recursive ones. So think about what happens on the line n equals q squared. Okay, so in this one, so if n is q squared, this is just saying like delta of qn is equal to delta of qn. Or this extra plus n doesn't hurt at all anyway. So we already know it's at least that big. So so this one just says delta of qn equals delta of qn, and then this one also says the same thing. So on the line n equals q squared, these two recursive bounds don't give you any information. And so the way the proof actually goes is you start with like a choice of n and q. You start with some sort of known bound, and then like maybe you start with a trivial bound, and then you extend one of the parameters to make it bigger, and then you apply the functional equation or one of these two results, depending on like which side you're on, and then you get a new bound out from that. And yeah, and then you basically you just keep applying this in succession, and you end up like in the limit you get the optimal bound by doing this over and over and over again.
Okay, so you're saying that in between we might have to use some other result just with these two theorems.
These two alone are not enough. You definitely need the monotonicity, because along the diagonal n equals q squared, these two things give you no information.
Okay, thank you.
Nothing there. Yeah, sure. Good question. Yeah, this came up in Heath Brown's quadratic large sieve as well. The difference is in his case, it's symmetric. Like his norm is symmetric, so he only really had to do. So he sort of gets like both of these results for free. Once he proves one, he gets the other one for free from symmetry, which is basically quadratic reciprocity. But in this case, it's completely asymmetric. So I had to prove these two results separately, and they're completely different proofs.
Hi, can you hear me?
Yes.
So can you go to your main theorem first one, I guess?
Yeah, let me see, maybe I can scroll faster. Yeah, where did that go? Yeah, there it is.
Right. So on the right side, there should be some factor. Have you normalized that? This L2 alpha?
Yeah, so this is why I defined it with this max over the vector of length 1.
Oh, they're normalized, you mean?
Yeah.
Okay. And so in the biased set, how much do you lose? So suppose you don't assume the condition.
Well, okay. So if you don't assume that the GCD of A and B is 1,
right?
Then you just basically you get q squared times the square root of n plus n.
Oh, all right. And is there any higher degree analog of this Einstein series? And is some result known for that?
So there, okay, so for like on, I mean, to some extent, so so for GL3 and or SLNZ, there's like for spectral families, there's this work of Blomer and Buckane where they got a lower bound for the Eisenstein series part, showing that part was pretty big. But maybe there's a biased set there that one could avoid with some extra hypotheses. So that's like the level 1 situation. So this problem is a varying level, and I don't think there's any results about varying level in GL3 or higher. So that's an open direction to work in.
So can you just vary T and level like the hybrid situation in your problem?
Yes, yeah, I did. Yes, exactly. And the result is optimal in that aspect. You could also have like characters modulo some fixed integer without like you could also throw in characters mod k for some integer k that's not changing with the problem, and then it's optimal in that in the k aspect as well. I just stated it like this for simplicity,
Like
to avoid having too many parameters.
hybrid version of this, like Gallagher hybrid version of this, like a by
exactly.
a by b to the it and integration of t.
Yes. Yeah. So that's there. I just didn't state it like this on the slide, but it's in the paper.
Oh,
So, which doesn't exist on the archive yet, but it should be fairly soon.
okay.
Yeah, and actually, I lied. I mean, I lied in the sense that like everything was overly simplified, and so even if you don't care about like this hybrid T aspect, you sort of get forced to put it in, especially on the. I think it comes from the family average side. Like you end up having to study more general values of like or impose a T aspect part of the problem, and so then. You really need closure properties under all these operations. That means you need to study this T aspect right from the beginning.
Yeah, thank you for the very nice talk. Can you go to the last slide?
Sure. This one?
Yes. So how do you proceed from there to prove your third theory?
Well, I mean, so I was being sketchy, but basically, so we used we switched the modulus and went to Dirichlet characters mod R. The Dirichlet characters mod R are not primitive, so you have to factor out the primitive part times the trivial part. The trivial part gives you a zeta. And so if you just, if you kind of squint at this and ignore this A1, B2 minus A2, B1 over QR to the S thing, like that's like kind of an analytic problem that the variables aren't separated there. But if you sort of ignore that, then this looks like what we started with. It's just the parameters are different. Yeah, so it's like if you're on the epsilon line or maybe -1 plus epsilon line, it looks similar to what we started with.
Okay, and a different question. You mentioned the arithmetic form of this rational large sieve. Do you have any application in mind?
No, not really. I've been looking. I'm looking for applications, but yeah, I have other applications on the horizon for a related problem that I'm working on with Ian Petro, but this is a kind of like the first step towards that. But for this particular one, I don't have an application. Yeah, I'd be interested, but I think anytime if you want to sieve rational numbers, then this should be helpful. Just like the classical large sieve is useful for sieving integers.
Yes. Yeah.
Yeah.
Okay. Thank you.
Yeah. Thanks.
Okay, any other question? Okay, so okay, Matt, it was a very nice talk.
All right. Thank you.
Visit India sometime.
Yeah, that would be fun. Okay. Let me stop sharing. Okay.
Okay, so we are closing this. Okay, let's thank the speaker again for a nice talk.